Hello, and thank you very much to the organisers for the opportunity to speak. I am here today to talk a little bit about knot Floer homology and braids. This is all based on joint work in progress with Day. Okay, so what is knot Floer homology? Knot Floer homology is an invariant of links defined independently by Ozra Sabu and Jacob Rasmussen, which takes value in the category of finitely generated graded vector space. So I'm not going to tell you too much about how it's defined, but I will say the definition uses simplex topology, and more significantly for us, it uses Hagar diagrams. All right, a couple of good things to know about knot Floer homology. Well, first of all, it detects the genus of a link. So the maximal grading in which knot Floer homology is non-zero is essentially determined by the number of components of the link and the Euler characteristic of the link. Furthermore, the rank in the top Alexander grading, so the largest one of which the knot Floer homology is non-trivial, is 1 exactly when the link is fibered. And so you can think of this as saying as well, if your link is too complicated to be fibered, then it has sort of high rank in the top Alexander grading. And we'll be returning to this idea of simple links having having knot Floer homology of small rank later on. Okay, so what about braids? Well, for me in this talk, at least, a braid is going to be a triple consisting of a surface together with a homomorphism, sometimes called a monodromy, which fixes the boundary of the surface point-wise and permutes some finite collection of points in the surface. Okay, so this is kind of an abstract definition. If you want something to get your hands on, well, you can think of it this way. So you have your surface up here, and you have the points in the surface. You take the product with the interval, you get a picture like this. And then what you do is you sort of glue the top and the bottom of this picture together using the monodromy phi. And well, when you do that, you get some kind of link called the braid closure from these three segments. Okay, so why have I bothered giving you this more complicated definition? Well, this more complicated definition makes it easier to extract Hagar diagrams. So how do we extract Hagar diagrams from such a triple? Well, what you do is you take your surface and you take 2 copies of it, one down there and one up here. And your points pi, well, you have a collection of points for each surface, you put dots on them. And for the alpha and beta curves of the Hagar diagram, what you do is you have this sort of standard picture downstairs. And upstairs you have the alpha curves are still standard, but you sort of perturb your beta curves by the monodromy. Fine. Okay. So using these sort of Hagar diagrams, Baldwin, Velovic, and Berteschi were able to define an invariant of the braids called the braid invariant, which takes value in the knot Floer homology of the braid closure. And well, this invariant has a number of nice properties. The one we'll be interested in today is the following. So if your braid, if the braid has closure which contains the braid axis, then your braid invariant is non-vanishing. So why is this useful? Well, this allows us to generalize the following result of Baldwin and Velovic. So they show that if K is a fibered knot, then the rank of knot Floer homology in the next top grading, this is the next to largest grading, which knot Floer homology is not 0, then that is at least 1. And to do this, they use something called the contact class. And so what we can do using the braid invariant rather than the contact class is we can show that in the next top grading of knot Floer homology with fibered link, well, that's a rank at least the number of components of the link. All right, so why do we care about this type of result? Well, this, together with a bit more work, allows us to show things of the following sort. So we can show that if your knot Floer homology is of rank 8, then you more or less know what your link is. In particular, if it's rank 8, then it has to be T2-4, T2-4, 4-component unlink, or the disjoint union of a Hopf link and an unknot. And I should say that, well, I've stated this rank 8 result, but there are corresponding results for sort of lower even ranks. Moreover, if you combine this work with Dowlin's spectral sequence, then you can recover some of Zhong and Shi's detection results for Kavanagh homology. All right, so I'll stop there. Thank you very much for your attention.